to make sure that when we randomize the order, we don't have the same person giving the last year's Neuroccino all the time. To make sure that when we randomize the order, we don't have this every time.
Yeah.
Right. I think we are complete for today. Michelle just texted he can't make it today. He scratched the car.
Huh?
He scratched the car.
Oh, shit. Shit happens.
Yeah. Right, apart from that, welcome to the final Neuroccino of 2024. And today we have Hervé present to us, all in the spirit today. Hervé, if you want to share the link in the chat and then
Yes.
take it away.
Yes, so let's put it here. So the usual, yes, let's put here. Let me share my screen. I can do it. Yes, I can do it. Okay, can you see it?
Yes.
Okay. So today. So this is Christmas. So I decided, okay, let's do something about related to Christmas. So let's find something. So Christmas is a time where you want to celebrate, you want to have good food, and certainly you want to have gifts. And when you are kids, what you are interested is a big gift. So here I present you elk, but I don't want to present something about elk, but what I want to present is something about a big MRI scanner. So today I'm gonna present something about the 11.7 Tesla that has been developed in Eurospin in France. So this is a MRI scanner that has been, yeah, as I said, developed there. So my interest is that, okay, so this is a big scanner, and a particular interest is because I was there not a long time ago, but during a period of time, I worked there in Eurospin, and I followed a little bit this project during the time I was there. Okay, so let's go to the article, which is not somewhere here. So why going to a bigger, big scanner? The reason for that is when you increase the B0 field, which is the main magnet field of the scanner, you improve the resolution and the sensitivity. So what you need to keep in mind is that with any kind of scanner, you can go to a very fine resolution with a very high resolution. But what you lose doing that is the sensitivity, the signal you will get. So when you increase the B0, you will get much more sensitivity, much more signal to noise. And so you can reduce the size of your voxel, so you increase the resolution. So why going to this resolution? So usually MRI scans are done to go to what we call a mesoscale. Mesoscale give you information on the region of the brain, on the structure, which is something which is not in details, but enough to study it. So you are in between worlds. So the one you want to go is you want to go to a micro scale when you can see the neurons, the connections. So what you can do is with microscopes, and you go to you do that on ex vivo subjects or ex vivo tissues. And and when you do MRI, I told you, you go to a macro scale. So you can do that in vivo. So the idea of this scanner is to go to in vivo and go to a mesoscale, so between these two scales. So it's why they developed a long time ago. The project started in 2001. And this is a collaboration between Neurospin and a lot of department of physics to build this magnet. And so they built this magnet, which is it's a large baby because it's 132 tons for this 11.7 Tesla magnet. Okay. So yeah, I told you they increase the B0 field. So let's look a little bit at the first figure. So they show you the size, the scale of this magnet. So you can see it's not a small one. So just for the representation, you can see here the subjects inside the magnet with the big magnet. So here you have the facility. The facility. I don't know if you can see my. Can you see my mouse or not? Maybe not.
Yes, we can.
Yeah. Okay. So you can see the facilities here, the scanner, and all the satellites of all the facilities that is needed for the scanner. So it's a 5 meter diameter magnet, and the bore where you put the subjects is now a 90 centimeter. So they built a dedicated arc to put it in. So you cannot put this scanner in a regular room. So you need to build a very large room for it. Here you can see an example of the copper wire that have been used to build the magnet. And if you go to Neurospin one day, in the entrance, you can see this large, what they call pancake, the magnet pancake. And the scanner is in fact piles of this pancake. Okay, so is the real room for the scanner. So it's just to show you that if a subject is scanned or patients, they will not see the difference because you cannot see the scanner. So you see something like that in the wall, which looks like a regular MRI scan. And here is the perspective one where you see that behind the wall, you have the big magnet. Okay. Losing my mouse. Okay. So let's back to the article. Okay, so as I told you, they increase the B0 field. What you get is better signal, yes, but you have different issues. The first one, when you go to higher B0 field, you get a lot of inhomogeneity issues. So you have them even in smaller magnet, but when you go to higher field, you have bigger magnet, bigger issues. So you increase the radio frequency, and so doing that, you increase the inhomogeneity of the images you get. So what they worked on that, and they use parallel transmission with specific call to reduce this problem, and they went also to higher the shimming to reduce the inhomogeneity when you scan. The other issue you get is the absorption rate. So the SRR, which is the specific absorption rate. So when you increase B0, you increase heating. So you need to be careful not to transform your MRI scan to a microwave. So which is good for the patient. So normally you don't get this kind of problem is a regular MRI scan because you monitor that. So here they specifically monitor carefully this absorption rate issue. So they got approval for scanning 20 healthy adult participants in 2023. And they got some scan from these subjects. So let's look at the image. Okay, so they scanned these subjects and they got really nice images with it. So here's a T2 T2 weighted image they got on the MRI, the 11.7 scan. So they use a kind of a regular T2 weighted image. So the resolution of this image is 0.5 by 0.5 by 0.5. So it's not something very extraordinary, but still. So they acquire this sequence. It's a 3D sequence in 13 minutes, sorry. And so what you can see on this image is the B0, the inhomogeneity, the lack of inhomogeneity. So I should have showed you what you get normally when you have a large inhomogeneity, but here you can see you don't see a loss of signal to the brain, so it's really homogeneous. So they want a little bit deeper. So this one is a 2D image, which is the resolution here is a 0.2 by 0.2. And so you can see that, for example, in the cerebellum, you can see real nice details on the cortex, on the different layers of the cerebellum. So that this acquisition was done in 8 minutes. Okay. So they compared what you can get on different scanners. So here you have the 3T, the 7 Tesla, and the 11.7 Tesla. So here what they try to do is to get something similar for the same amount of time. So the three images are done in 4 minutes, and they try to keep the similar contrast to noise and also the same, and they adjusted for acquisition parameters and also for spatial resolution. That means you don't see the same. This is not the same resolution for these 3 scans. The only thing similar is the time. So here the resolution is 0.5, here is 0.3, and here 0.2. And you can see the increase, what you can get with an 11.7 Tesla in terms of resolution. For example, in the occipital cortex, in the visual cortex, where you can start to see the different layers, cortical layers. Okay. Okay. So as it's as 11.7 Tesla is kind of uncharted territory, they wanted to look at different effects you can get. So the first one was the vestibular effect. So when you go to, for example, 3T and even more in 7 Tesla scanner, you can have vestibular effect. You can when you get out of the scan, you can be a little bit unbalanced. And so that is due to the interaction between the magnetic field and your vestibular system. So they wanted to test that. So they test the balance. They did a balance test before and after the scan. So they ask volunteers to stood for 30 seconds, eye open or closed on a platform dedicated to test the balance. They didn't see any changes before and after. They also look at the genotoxic effect. So if you stay too long in a magnetic field, you can damage your chromosome. So let's be clear, it's not happening when you do regular scans. It's happening when you stay a long time. They wanted, as 11.7 Tesla is not, it's not a regular scan. They wanted to test that to be completely sure that it was clinically valid to do that. So they tested. So they took a sample of your blood before and after the scan. And here again, they didn't see any changes of the chromosome damage. They did not detect any chromosome damage in human cells before or and for sure after. So what they did more, it was to look at the behavioral or the cognitive effect on the 11.7 Tesla. And so what they did, they took the flunker task and they did the flunker task before, during, and after the scan. For those who are not familiar with this flunker task, it's a attentional task where you ask the subjects to decide in which direction is going the middle arrow. So you can have incongruent situation and congruent situation. So they had two samples of subjects, so 20 and 20. 20 had these task on the 11.7 Tesla, so before, during, and during with noise, and out. And the other sample of subjects, the other 20 subjects, are the same thing, but in a fake scanner. And they put some speakers behind the scanner to make some MRI noise, to mimic the sequence, the noise that is making the scanner when it's doing sequences. So here's the decision time. And here's the flunker cost. The flunker cost is the difference in decision time. The difference in time between the incongruent and the congruent situation. And so here I didn't see any differences for this different situation for the for the group for the 0 Tesla and the group in the 11.7 Tesla. Okay. I'm in time. Okay. So something it's worth noting is that so they had 20 subjects and 2/3 of the high resolution scan were corrupted by motion. So that means a few scans were okay. So that is a problem when you go to higher resolution, because you go higher, but the subjects need to be very still if you want to go to this resolution. So if the subjects move a little, it will create some motion artifacts. So the next steps on this scanner will be to develop some tools to correct for this motion correction and to accelerate the sequence to get something with higher resolution with less time. Something I didn't talk about it. So what I showed you and what they showed you in this article is T2 weighted images, which is mostly for neuroanatomical purpose. But what we would like to see is more functional, for example, functional MRI and also diffusion MRI. So that they need to work on it, because not only you need a very big B0 field, but you need also gradients to be important. So you need powerful gradients to work on it. And okay, so they conclude on the purpose of this big scanner, the applications. So what it can be helpful in the framework on application, like clinical application in the situation of neurological disorders or psychiatric disorders, where you can go to something which is can be interesting, like I told you at the beginning, where you can go to a mesoscale, where you can close the gap between the microscopic scale and the, for example, circuits, neurons, and synapse, and the macro scale, where you look at, for example, connectomes or macrostructures, and when you can close this gap. I hope I was clear. I have nothing to add, I think, except Happy Christmas. And ready for some questions, for sure, if I can reply.
Amazing. Thank you so much. It's always a pleasure listening to your presentations. First hand up, Eduardo.
Yeah, thank you. Have a very nice presentation. It's also curious to see that they finally have some data from in vivo people. My question is, how do they deal with the displacement of the tissue related to the pulsation of the blood vessels?
Good question. They didn't talk about it. I don't think I saw something about it. Yeah, I didn't see it. So it's a really good question. I didn't think about it, so I don't know how to reply to that. So it can be an issue. Uh, you mean for the functional or even for the anatomical scan?
Well, I guess it's more acute for the functional scans, but
Yeah.
for such a teeny tiny voxels, maybe it's a problem also for the structural ones.
Yeah, it
I
can
don't
be.
know.
Yeah, I didn't see anything about it.
Interesting.
So they need, yeah, the end of the paper. So it's a short paper. It's a short communication. They just say that they need to work on these increasing performances for perform high resolution functional MRI. Maybe it's a package who say that they need to correct for it, but I don't know.
Okay, thank you.
Eva has a question as well.
Hello, thank you for the presentation. It's not so much exactly about the presentation, but more the genotoxic effect that you mentioned.
Yeah,
How long exactly, or how, because it says repeated exposure, so how
yeah.
many times, or
To get this. I don't know because the paper they cited is on mice where they put mice during a long time on a magnetic field, and when you can see this kind of effect. So I think they wanted to be sure that they didn't get this effect on because it's chronic. Normally you get that on chronic, but as you increase the B0 field, they wanted to prove that increasing the B0 field is not impacting these effects. But I don't know on this paper how much was it? I don't know. Where is it? 16. Yeah, this is into. I think even this paper is more. It's a meta-analysis where they look at different papers that studied that, and there is no conclusion about this effect. So, but yeah, they wanted to
okay.
ensure that was not affecting their project.
Mm-hmm. Okay, thank you.
Actually, related to that, you mentioned that they took blood samples to
Yeah.
check. I was wondering if they also looked for cortisol levels, because the setup of the scanner is also interesting, right? Where you have the wall, and if you go in, you basically go into a wall. I can imagine that's also
To
quite
another world,
idea-inducing.
and you see Santa Claus when you go inside.
Best case scenario.
But yeah, I show you the pictures. If we go back, I don't. Yeah, if you are claustrophobic, it will be anyway a big problem. But for me, it doesn't seem to be so much different. When you go to MRI scan, you see this kind of situation. I don't know if it will be more careful. At the beginning, so when I was there, there was no wall, and that was really scary because the machine is really big, and you need to imagine, yeah, you go to this, you are a teeny thing going to this big thing. But now when I see this picture and when you enter the room is small and you go inside. I don't know. But to reply to your question, I don't think so they have questionnaires on the subjects, but I don't know if they ask if the subject was scary and stuff like that. So they didn't check that, but they could because they have the blood sample. But yeah, I didn't see anything about that.
Okay. I don't know who was first. Muge?
Yeah, thank you. Yeah, thank you, Hervé. It's very interesting. I'm curious about this. I have two questions. So first question is, why is this arbitrary number like 11.7? So after 7 Tesla, what happens when it becomes 11.7, but not like 10 or like 12? That's one question. Yeah,
Yes.
and then yeah, other one is I was curious, like, because the more you increase the Tesla, the more like artifacts you get around like ear cavities and stuff. So do they mention like how do they deal with that susceptibility issues?
So that will be more okay. Let's start with the. So I don't know for the 11.6. I think it's a technical. I mean, you can go. I mean, you can go. I think they selected that because yeah, it's a good question. I don't know if they had in mind something or just let's go to 3, 7, and let's put 3, 4, 5, 4. Let's go to 11, 11.7. I don't know. Maybe physicists will
Yeah.
reply because
There's a project in Nijmegen now. They are like planning to build a 14 Tesla, for example. But yeah, in between like 11.7 sounds so like I don't know, like
yeah,
very.
so maybe it's the size because you need to the size. There is a whole story I didn't show you, but to bring these magnets were not built in France, they were built in Germany, and to bring them back in Europe, they didn't take the train, they took the boat. So the boat went back to the sea and to the Seine to come back, and so there is a blog. You can see the little trip of the scanner going through the Europe. I think it's part of the issue because when you go to big magnets, you need to move these magnets. So that is the first thing, and maybe the other thing is related to the second question. The bigger you go, the bigger is the problem you get. So maybe they say at this there is a balance where you can get high field and not so much problem with it. So maybe that was the answer. For the susceptibility, it will be a really, really big problem for functional MRI or even for diffusion because what you normally use is API sequence when you have these susceptibility artifact due to the, like you say, when you have a big change between, for example, air and bones, and you get really big distortions. So you can correct for, like they said, if you do parallel transmission, you can kind of mitigate a little bit these effects. They didn't show any functional MRI, so that will be a really big problem for them to correct for that. But let's see, maybe they will manage that. So the question is, yeah, applications. So how you can apply so that, yeah, because now in clinical setup, you are mainly three Tesla. And now I don't know if the thing is to go higher in a clinical setup. So maybe 3 Tesla is enough. But if you want to go to a mesoscale, you need to think higher.
Mhm. Thank you.
So you mentioned diffusion imaging, but is there really a push for diffusion imaging on the 11.7? Because like diffusion gets better with more gradients, not
Yeah.
necessarily with more.
The thing is, yeah, it's what they did for the human connector project. They built specific gradients for this project because you can have a very big Bezier field, but what you need really is really big gradients. So you need very big, small. So the gradients are around the big the Bezier field, and what you do specific sequence where you change the gradients to get the water diffusion, and they didn't. So maybe they need to build something around the scanner, or they need to change the gradients. I'm not sure about it. I think I know they work a lot on diffusion on this on there, but I think the main idea was to go to really small details, micro scale, mesoscale, but to go to the different layers of the cortex and only about neuroanatomy, not diffusion. So that,
Given the last author of the paper, I expect some diffusion insights.
yeah, for sure. So yeah, I don't know. Yeah, for that I didn't follow really carefully what they are doing now. So
Fantastic. And then one question that came up in the chat as well was when you showed the images of the 3T, the 17, the 11 point, 7. You can also see it here. Actually, if you go back, you can see it better. Yeah. So we're still losing signal in the orbitofrontal cortex here, right? So is this image
Yeah,
fully corrected, or?
yeah, no, it's fully correct. For me, it's not. Yeah, you are losing signal. Maybe it's still a problem. But for me, it was not so bad. Yeah, you lose a little bit, but here you don't see. And you say on the other one.
Yeah, it was more that image actually.
Yeah, a little bit. Yeah, you should. Yeah. But for the T2 is not shouldn't. Yeah, it's a T2 weighted. So, but it would be not. This signal will be a problem for functional MRI scan. On T2 is not. It's not so a big issue. So I don't know. Yeah.
Okay.
Do
That's
you know
cool.
if this would also higher fields are beneficial for things like myelin imaging?
For T2, yes, for T1. The thing is, when you do what they call relaxometry, for example, T1 or T2 relaxometry. When you want to do that, so you want to have a complete relaxometry of the relaxation of the T1 and the T2 parameters. And so when you go to this higher field, you will get really nice signal on these parameters. So yeah, it will be better. Yeah, it's true. They talk about it, but yeah.
They do or they don't?
They don't. I
Oh.
didn't see. Maybe I'm missing, but I don't. I didn't see.
Mhm. Thank you.
Lovely. That's all the questions I can see, and that concludes the Neuroccino series of 2024. Thank you so much. Thank you so much for joining today, but generally this year, and for presenting so many exciting papers. Whoops, sorry,
Sure.
didn't mean to stop your video. And wish you happy holidays and see you again in January for the new season of Neuroccino and CNS Talks for that matter. Have a good break. See you soon. Bye.
Bye.
Thank you. Bye.